History of Vector Analysis, Episode 6, Hamilton and Triplets. You are here. Hey, Soul.Golder, here to bring you more unbridled joy and suffering. Last time I talked about how Caspar Wessel and then the legendary Carl Friedrich Gauss showed that there was a geometric interpretation for complex numbers, at least if you postulated the existence of the complex plane. In the process, these guys inadvertently created the first vectorial system, an algebraic/geometric hybrid in which certain types of mathematical objects could be thought of as having a magnitude and a direction, as well as coordinates. This interpretation was limited to two dimensions, namely the real and the imaginary, but there were a number of people at this time in the early 1800s who recognized that a three-dimensional version of the complex plane might have all sorts of useful theoretical and practical applications, seeing as how reality seemed to be comprised of three spatial dimensions. The first of the two people that Michael J. Crow discusses in his History of Vector Analysis is a guy named Hermann Gunther Grassmann. I'm not going to spend any time on him because, as Crow notes, it was not his work that influenced the course of mathematical history. That credit belongs to the second person Crow writes about, William Rowan Hamilton. It is to him that we will now turn. Hamilton was an Irishman through and through, born, worked, and died in Dublin. Hamilton can be placed with Mozart as a successful former child prodigy, albeit in mathematics rather than music. He was appointed professor at Trinity College in Dublin while he was an undergraduate there. He was named Official Royal Astronomer of Ireland at age 21. We wouldn't be talking about him today if he had peaked at age 21, as so many child prodigies sadly do. His most famous physics work came in the development of the principle of least action for mechanics, building on the work of Newton, Euler, Lagrange, and others. If you have taken a 300-level classical mechanics class in college, you will have spent time living and breathing the Lagrangian and Lagrangian mechanics. As Wikipedia notes, paradoxically, the credit for discovering the quantity now called the Lagrangian and Lagrange's equations belongs to Hamilton. He also developed the Hamiltonian version of classical mechanics, the canonical equations of which are shown here. In classical mechanics, the Hamiltonian operator is used less often than the Lagrangian operator, but it turns out that the former is highly applicable to quantum mechanics. So the term Hamiltonian in the Schrodinger's equation refers to this guy. He was knighted, even though he was Irish and not English, in 1835 at age 30. But none of that is the subject of today's episode. In 1831, Carl Friedrich Gauss, then the biggest name in mathematics by far, gave a presentation to the Royal Society of Göttingen in what is now Germany, where he discussed the complex plane and what he called the double algebra of complex analysis. This was the presentation I discussed in the previous episode in which he coined the term complex numbers. The presentation was published as a memoir, and Hamilton got a copy of it in the mid-1830s. He was intrigued. Hamilton was one of a handful of mathematicians who tried to extend Gauss's double algebra into a three-dimensional triple algebra, motivated to a degree by a view that a 3D algebra in a 3D world might offer some practical applications. But Hamilton's primary motivation was philosophical. He developed and latched onto the odd metaphysical view that a triple algebra could be to time what Euclidean geometry was to space. Hamilton was a big believer that mathematics was science, truth, and/or reality. It might be said that he was more Pythagorean than Pythagoras himself. This view was not well received. The community respected Hamilton's brilliance and his stature, but by the late 1830s quietly began to wonder if he had lost his mind. He was in fact drinking pretty heavily by then. Tragically, it seems that brilliance cannot buy happiness. Hamilton's first paper on complex numbers and triplets appeared in 1837, some 6 years after Gauss's memoir. It bears the long and unwieldy title, Theory of Conjugate Functions or Algebraic Couples, with a preliminary and elementary essay on algebra as the science of pure time. In it, he argues that the use of complex triplets instead of couplets was required to bring this to fruition. As the title suggests, the primary focus of the paper was metaphysical. No one bought into this, even at the time. But Hamilton was recognized as sufficiently great that his paper couldn't be dismissed out of hand. And it turned out there was some interesting mathematics embedded in it, even though he never could bring his theory of triplets to any sort of completion. Importantly for our story, the paper introduced the significance of the commutative, associative, distributive, and inverse properties when considering mathematical objects and operations. This was something that mathematicians had not seriously considered before, since up till that time, algebra satisfied all of these, even with complex numbers. Here are some images of what Hamilton proposed. The complex plane of Wessel and Gauss had two axes, one real, one imaginary. If you want to extend the concept of multiple algebras to 3 dimensions, you need a third axis. How do you approach this? Is there a type of number in addition to the real and imaginary that you can use? If so, how does it behave? It's pretty crazy stuff. Hamilton's approach for the tricky third axis of the complex plane is not this one on the left with x, y, and z. He does not use 3 real axes, nor 1 real, 1 imaginary, and 1 extra imaginary axis. Rather, he takes the approach of 1 real axis, 1 imaginary axis represented by the letter I, and a second imaginary axis represented by the letter J. His vision was that I squared equals -1 and J squared equals -1, but that I was not equal to J. You may be excused if your first reaction to seeing this is WTF. Euler had shown in the 1750s that one of the few pros of these weird complex numbers was that the set was closed under pretty much all operations. The square root of a complex number is still a complex number, and I to the pi is too. The mathematical community may or may not have breathed a collective sigh of relief that, after going through irrational numbers, and then negative numbers, and then complex numbers, that the ordeal was finally over. No new types of numbers need to be added to mathematics. Yet, here was Hamilton introducing a second imaginary axis anyway? This seems worse than useless, but let's continue. Okay, fine. 1 squared is still +1. I squared equals -1, and J squared also equals -1, but I is not equal to J. So, this begs the question, what is I times J? Hamilton runs into this problem almost immediately. Hamilton's addition of his triplets starts out fine. This isn't quite the notation that Hamilton used, but it's similar. Let us define T1, T for triplet, as a real component characterized by the coefficient W1, and an I and a J component characterized by the coefficients A1 and B1, and then the same for T2. Following this approach used for complex numbers, he adds the 2 triplets like this, and then goes off and gets this, which is a satisfactory T3. He sees that, at the very least, T3 has the form of another triplet, a real component, an I component, and a J component. So far, so good. Now for multiplication. We define T1 and T2 as before, and now we multiply the two using the standard cross multiplication technique. When we did this for complex numbers, which have 2 components, we ended up with 4 terms. Triplets have 3 components, so this process will produce 9 terms. I'm going to go through the arithmetic slowly, step by step, because I will use the algorithm I show you here for more complex problems going forward. The first step of the algorithm is to produce the 9 terms. There are many ways to do this, but the approach that I will always take is to multiply the first term of the first triplet by the entire second triplet. Okay, this by all of this, and that gives you this. Then repeat it for the second and the third terms of the first triplet, creating this and this. Now, we don't know if the i's and j's commute. It will turn out that they do not. So we have to be very careful about the order we write the i's and the j's in when we have more than one of them. On the other hand, we do know that the real numbers, which includes the w's, the a's, and the b's, do commute, so I am free to exchange those as I see fit. Generally, what I will do is to put the real coefficients in subscript order. First the sub 1's, indicating that they are from the first triplet, and then the sub 2's, and then the sub 3's if there are any. There are other ways to do this that yield the correct answer, but this is how I'm going to organize these terms going forward. The next step in the algorithm is to leave the terms in exactly the same order, but to evaluate the products of the plus or minus 1s, plus or minus i's, and the plus or minus j's. Hamilton assumed that anything times 1 equals itself, and by Hamilton's other rule, I squared and j squared are equal to -1. But here it is, with the question marks. How do you handle the mixed ij and ji terms? For the moment, we'll leave them alone. The third and final step of the algorithm is to regroup the terms into similar kinds. Those that are real, those that are proportional to I, those proportional to j, and in this case, the ij mixes that we haven't resolved yet. In order for Hamilton to consider triplet multiplication to be well-defined or well-behaved, which is important to a guy seeking truth with a capital T, he really needs the product of these two triplets to remain in the set of triplets, that is, be of the form w plus ia plus jb. So we have to resolve these cross-product terms. So Hamilton is effectively here. T1 times T2 equals something that is not quite of the form T3. A subtle but important point is to note that we didn't have this problem with complex numbers. Z1 times Z2 came out unambiguously to Z3 with no hybrid real imaginary terms. So we are in uncharted territory here. Hamilton needs to discover, that's the way he looked at it, he had to discover what the true values of I times j and j times I are. What are his options? Well, he can discover that I and j are the same after all. Then ij equals ji equals -1. There's a couple of problems with this. The metaphysical one is, if I and j are the same, do you really have two independent imaginary axes? Another is that you would then have 5 real terms and only 2 I terms and 2 j terms. This asymmetry rings false. Rejected. You could try ij equals ji equals +1. This cleverly infers that a distinction between I and j exists, since I squared equals j squared equals -1, but I times j is not equal to -1. But it still has the same asymmetry problem. Rejected. You could try to find a way to get these two terms to cancel each other out, kind of like what Cardano did when he first studied the square roots of negative numbers. The obvious tactic here is to try to discover that ij equals -ji so that the two mixed terms have opposite signs. The problem here is that the magnitudes of these terms aren't equal. Okay? A1, B2 is not in general equal to B1 times A2. So this has to be rejected also. We can perhaps start to smell Hamilton's desperation. All right, let's take the gloves off. How about if we discover that ij and ji are both 0? That would solve the problem, wouldn't it? Well, it would eliminate the two troublesome terms, but you still have an asymmetric number of terms in each group, 3, 2, and 2. According to Crow, Hamilton spent a lot of time and effort exploring this route, but apparently it led to other problems later on. He eventually rejected it as well. Long story short, Hamilton spent years with this problem as his top priority, trying to come up with a practical, internally consistent triple algebra, one that can support all arithmetic operations. In 1843, 6 years after his first triplets paper, he discovers that almost all of his problems can be resolved if, get this, he adds a third imaginary axis, making 4 total. He will call these new mathematical objects quaternions, and he will spend the rest of his life working on them. Several decades later, after a few plot twists, modern vector analysis will rise out of it. Spoiler alert. Quaternions will go through a slow rise and fall, but they will never go away completely. In fact, they are now widely used in certain types of navigation equipment and navigation and animation software because they handle the modeling of rotations on digital hardware efficiently. In closing, I want to reiterate that Hamilton fervently believed that he was not just making this stuff up. Rather, he believed that he was trying to discover the correct path through the metaphorical maze. There was a pure, true answer, and he intended to find it. The development of modern vector analysis, as we will see, holds no such idealistic views. Coming to understand and appreciate this, I hope, is something that will help the troubled physics major be a little less troubled. Okay, in the next episode, we're going to get dirty and we're going to wade into the guts of Hamilton's quaternions. See you then.